Okay, so let's get started. Uh, so the the detector that the detector that um, minimizes P for any prior probability is termed the maxima a posteriori detector, MAP detector. Then, of course, for equal prior probabilities, the MAP detector reduces to the ML detector. Okay, so this is like the maximum likelihood, but it's true only if the prior information pH0, pH1 is equal. Otherwise, they won't be equal. Otherwise, it would be like what? Otherwise, it would need to be like this, like this. Okay. So this maxima a posteriori probability. The decision regions for the DC label in WGN for this is for illustration purpose, so we try to make it simple. The decision region for the DC label in WGN with n equal to 1, a equal to 1, sigma square equal to 1 are shown in figure 3.10 for various prior probabilities. For example, in here, if you have a uh, let's look at here. Look at the comments, the caption. Effect of prior probability on decision regions. If it's equal prior, then it's trivial, right? 就像是我们第一章讲的 ，this is a trivial case. We set a one half. But if it's unequal prior, then with what? With this calculation, with this calculation, then you will find that the uh, the the threshold seems to deviate from one half. Originally, it's supposed to be here. Now it deviates to here. Deviates to here, right? The reason is that if you have h0 1 over 4, h1 3 over 4, then we have a problem. What problem? The h1 occurrence has higher probability. Therefore, you have to be you need more evidence, right? You need sort of needs a very more stronger indication to make you decision on H0 because H1 has stronger information, has stronger prior。我用中文讲一次哦，就是 H1 它的 prior probability 比较强，比较大，所以要让你决定 H0 是不是相对的更困难呢？因为 prior 比较大嘛，所以如果你要决定这个 prior 比较小的东西是真的的话，那意味着 sample 告诉你的事情要比较强烈的支持 H0，你才会决定 H0。As a result, it deviates from one half to minus 0.6. Of course, the calculation can be done by previously we have decision rules here, right? We have decision rules here. So you can do the calculation here. But the calculation is one thing, the interpretation is another. So what we like to do is to show you the implication. You need a stronger evidence to make you decide on H0. Otherwise, you always say H1. As a result, it goes from here to here. Okay, so this is like a stronger implication and it consistent with our our intuition。举例来讲，如果有一个东西它的 prior 是0.99，另外一个是0.01，那你就需要很强很强的证据，你才会说哦是 H0。因为为什么？因为 H1 的 prior 是0.99，哦，那非常高哦，那你几乎是可以非常相信说 H1 发生的机会很大啊。那为什么我今天要选择 H0 呢？就是因为你观察到的证据说，实在是很强烈的支持 H0 这样子。Okay, so this is an example. You see that the threshold deviates to here. So you decide on H1 for all this region and then decide H0 on all this region. Oh, okay, so the point is I want you to understand the calculation, the concepts behind those detections and mathematics calculations, and also the implications behind those calculations and numbers. Okay, so then the next thing is base rule. 所以我们在第80页 base rule. A generalization of the minimum PE criteria assigns costs. So now we are introducing one more thing, which is the concept of cost. So, as an example, if our detection is to inspect a machine part, and the result of the inspection is either to use the part in a product, if it's deemed satisfactory, or else to discard it, we will set up the hypothesis test like this. H0, the part is defective. H1, the part is satisfactory. Okay, then then you see in this kind of scenario, you start to have a concept that has not been introduced before, which is the cost. 就是我们开始对于每一个决定开始有了一个成本的概念。好，你可以回顾一下我们刚才讲的一系列的想法。一开始我们只说你收到 sample 叫你猜 H0 H1，这最简单的形式。第二个形式就是开始有 prior 跑进来，就是你还没有收到 sample 的时候，你都会有，可能会觉得有 prior。像我举的最明显的例子就是沙漠那个例子，因为我们台湾下雨的几率有时候是一半一半，所以你的感觉可能不明显。好，因为有时候一半下雨，一半不下雨，所以有时候刚好 equal prior。那我如果说，非洲沙漠的叫你说，有没有下雨？我们距离这么远，你也没有办法拿到 sample，你大概会说不下雨，而且你对的几率大概是95%，这就是 prior。Now we start to have something more cost because when we make a decision, we have to take actions. For example, if it's in a factory, when you decide H0, you take some actions. You decide H1, you take the other actions. And those actions brings benefits and cost. 这些不同的决定跟动作都会带来成本跟效益，所以我们就开始引进了这个成本的概念。Okay, so we are at page 81. So, and also we assign costs to the errors. So we let Cij be the cost if we decide Hi, but Hj is true. So for example, we will probably want C10 larger than C01. If we decide the part is satisfactory but it proves to be defective, the entire product may be defective and we incur a large cost. If, however, we decide that the part is defective when it is not, we incur the smaller cost of the part only. So once costs have been assigned, the decision rule is based on minimizing the expected cost of base risk R. Of course, you can talk about different scenarios, and different scenarios is going to give you different cost structure and different benefit structure. I want to clarify one thing, that the cost uh, uh, is actually human definition，它是人为的一种决定。You can say that I set the cost to be positive, meaning cost, and then I minimize it. Or I will say I set the cost to be negative, and then I maximize it. I think it's the same thing mathematically. So the cost and minimization is the sort of artificial human interpretation. And you can set it different ways. I think they are all correct. They are all correct. Okay, but here we just follow the textbook by saying that the cost is set as positive, and then we minimize the cost, or we say base risk. Okay, so then mathematically the base risk R is defined as R equal to expect of the cost, which is equal to summation I over I, summation over J, then its cost multiplied by the types of the probability of the errors. The probability of errors has been said and explained in previous chapter, right? It's prior multiplied by the mistakes, the probability of making mistakes, right? This is the probability of this type of error being occurring, and then multiplied by its cost, Cij, and then you sum over all possibilities. You sum over all possibilities, right? Okay. Usually, if no error is made, we do not assign cost to it. However, for convenience, we will return the more general form. Also note that if C00 is equal to C11 is equal to 0, C10 is C01 is equal to 1, then R is equal to PE. This can be proven. It can be proven. And its implication is in digital communications, when you are making a decision for correct detection, you don't have cost, but you make an error, you have a cost of what? You make a 0-1 error, you make a 1-0 error, it's the same. 就是你把零的变成一或一变成零，它的结果是一样的。So the costs are all one, and then you will see that this cost is in fact equal to PE. PE. Then under the reasonable assumption that P10 larger than P00, P01 larger than P11, the detector that minimizes the base risk is to decide H1 if something like this. Then again, this can be proven, but we are not going to do it here. The conditional likelihood ratio is compared to a threshold. Okay, so then we can recall that without introducing prior, we don't have, no, just make a correction. Without introducing the cost, we actually do not have this term. Then after we have a cost, the cost actually comes into play, and then it becomes part of the threshold. So we can return back to here, page 78. We see that the ratio of the prior is the threshold. Now, now we add more things into it. We add cost. Now cost becomes part of the threshold. So uh, the minimization of the base risk is to set the threshold this way and then compare the likelihood ratio. And then we make a decision. If the likelihood ratio is larger than threshold, then that decision will minimize base risk. This can be proven, but we're not going to do it. But to summarize, if you do not have a prior, you do maximum likelihood, then you still do uh, likelihood ratio larger than 1, right? That's the maximum likelihood. The second thing is, if you have prior without cost, you do likelihood ratio larger than the threshold, which is uh, the ratio for the prior here. That's the second thing. The third thing is, if you have a prior and you have a cost, you want to minimize the cost, you still do the likelihood ratio, but compare with the threshold that includes cost and prior, and then you minimize the base risk. So that's sort of the Bayesian cost idea. OK，这个 cost 的观念很重要，因为在不同种类的工程问题、研究的问题里面都会有 cost 的概念。那譬如说举例来讲，如果大家做影像处理的，可能常常会遇到那种需要辨认猫一个图案里面有没有猫、有没有狗那种问题。哦，那你可能要思考说，如果辨认错误所引发的 cost 是什么，对不对？因为，比如说把猫辨认成狗，或把狗辨认成猫，诶，那到底对于使用者的情境来讲，它引发的，也许引发了不愉快的感觉，引发了什么？这个像电子商务里面，如果你辨认错误的话，你可能就失去客户啊，失去客户就失去一个赚钱的机会啊，等等，这就是有 cost 的。哦，OK，so let's say if 如果你想要辨认，想要推荐一个客户某种东西，结果推荐错误，推荐错误当然就损失做生意的机会嘛，好，所以这就是有 cost 的，所以这在很多不同应用里面就是有 cost 的结构这样子，啊。那就像我刚才讲的，cost 是因为我们这里把它设定成正的，所以我们才 minimize 它。你也可以把它设定成负的，然后 maximize 它，也是可以的。好，OK，so let's continue to the next chapter, which is the multiple hypothesis test. I think multiple hypothesis is a very important one, and it's more general. 它是更一般化的对问题的描述，相较于我们先前都谈 binary 的问题。We now consider the case where we wish to distinguish between hypotheses and that is larger than 2. Such a problem arises quite frequently in communications in which one of signals must be detected. For example, if you have a 4 quant, the is equal to 4. If you have 8 quant, then the is equal to 8. Things like that, right? So you actually have multiple hypothesis testing. In image processing, there is also a lot of problems that are multiple hypotheses. For example, if you are given a picture and you want to detect whether there is a cat, there is a dog, there is a tiger, right? There is a sheep, there is an elephant. Then you have 5 hypotheses, right? If you have different animals to be detected, then you have many different hypotheses. So for example, another example is if you want to detect a person in the image is either female or male, 是男生或女生, oh, then you have 2 hypotheses. but you want to detect this person is let's say he's below age of 10, from 10 to 20，你要辨认一个人的年龄 from 0 to 10, 10 to 20, 20 to 30, 30 to 40, so on and so forth. Then you have multiple hypotheses, right? So it really depends on the scenario and problems. But as you may know, this multiple hypothesis is a more general version of binary problem. Alright, so pattern recognition，就是这个 pattern recognition，就是我刚才说的那一种，make extensive use of results in distinguishing between different patterns. In addition to signal detection, the problem is also goes by the name of classification, discrimination. If you read the papers in machine learning, in artificial intelligence, or in image processing, you see a lot of words, classification, discrimination, and sometimes if you have learned the course of linear programming of convex optimization, right? You see some vocabularies in classification, discrimination, SVM, things like that are all dealing with this kind of problem. But what we are dealing with is a simple form of the problem, but we have a more systematic way to deal with it. Although an NP criteria can be formulated for the M-array hypothesis, we call it M-array hypothesis. It seems to be seldom be used in practice. The interested reader should consult for further details. More commonly, the minimal P criteria and its generalization base risk is employed. We now consider rate. Assume that we now wish to decide among the n possible hypotheses, H0, H1, H2, H3, so on and so forth, all the way to Hn minus 1. The cost assigned to each decision to choose Hi when Hj is true is denoted by Cij. So, in other words, if j is true and we make a decision on I, we are making an error. But here, the more important thing is we know that this is the cost or benefit associated with it. We think of it in a mathematical way rather than engineering way. Okay, for now，暂时先用这个数学的想法去想它，那比较容易理解。But the interpretation, of course, is up to the engineering scenario. The expected cost of base risk will become this way. You have prior multiplied by the decision type, which can be correct, can be incorrect, and then cost associated with it. And you summarize over J, you summarize over I, then for particular assignment, Cij will be 0 if they are the same. In other words, this is a simple example by saying that if you make a correct decision, there is no cost. But if you make an incorrect decision, there is a cost. No matter what kind of error you're making, its cost is 1. So this is a sort of a simple particular assignment. But again, if you have different type of engineering problem, you may have different settings. Then we have R equal to PE. Think about it. Think about it. 如果你这样设定的话，这个东西就变成了是 error，就变成是 error 了。就是 probability of error 啊，就是通讯系统里面在讲的那个 probability of error。但是就像我讲的，你不同的工程问题，你会有不同的想要设定的方式啊。譬如刚才举例说，you don't want to lose customers because you recognize that person incorrectly, right? 这个人假设他喜欢猫，你推荐他狗的东西，哇，那你就失去客户了，那是损失了一些利润，这样子很可惜啊。所以每一种 setting 会有不同的这个 cost 的结构。 The decision rule that minimizes R is derived in appendix, but we skip it now. It shows that we should choose a hypothesis that minimizes this over I equal to this. So what this means is we're going to choose a hypothesis. We're going to choose a hypothesis that minimize the cost. This sort of the cost multiplied by its probability. In other words, it's the average. We can think of it as the average cost or the cost of the expectation of the cost. So we are going to minimize it. Choose a hypothesis that minimizes the overall cost. Then overall hypothesis. To determine the decision rule that minimizes P, we use 3.20. Then Ci of x is equal to this. And how come is P would look like this? Because we have this assignment for the cost. Then we put it into here. We will simplify it. We simplified it. Okay, we simplified it. Then we have a Ci of x equal to something like this. Something like this. And then uh, of course, this only applies for I not equal to j. If it's equal to j, then Cii is 0, Cjj is 0, so it disappears. And then it goes like this. It goes like this. Then, since the first term is independent of I, Cix is minimized by maximize P Hi conditional x. So the first term is independent of I, this term. So in other words, if we want to minimize the whole thing, we maximize this thing because it has a minus term in front of it. Therefore, the minimum P decision rule is to decide HK if this is larger than that. If for all K, for all for all I, HK, P of HK conditional x is always larger than P of HIX, then we decide on HK. Okay, so this is similar to the likelihood ratio, right? If you divide this to here, it becomes a likelihood ratio larger than 1. But it has to be true for all I not equal to k. In other words, if we have many hypotheses, we are choosing HK that has the maximum likelihood. It's the same word, maximum likelihood, except that other than the binary case, we have multiple hypotheses to be compared rather than just one. Okay, so up to this point, we take a break and we will come back.